So everybody present, सब लोग आगे, हाँ? So first of all, I would like to introduce myself. I am Professor Shivayan Sarkar, Associate Professor of Mechanical Engineering Department, IIT ISM Dhanbad. My actually research area is hydraulic turbine, water resource, pipe network, and mostly fluid mechanics and fluid machines devices. So I would like to thank you because you have come across the country. Thank you all. So we'll start our next session. This session is for 1 hour. We will discuss about the materials of the hydrokinetic turbine. So here you can see there are different components of hydrokinetic energy system. If we consider, there must be some powerhouse, there must be some distribution system, as well as there must be, here if you see here in this particular figure, here you can see, just hold on a second. So this is the distribution system, this is the river, here this is the structure made. This type of structure, it is called converging diverging section. So this converging section is generally made in order to increase the speed of the fluid which is passing through the river or channel. So basically what we are doing, we are contracting the channel. So whenever the river flow area getting reduced, so velocity of this river, that will be in the river flow, that will be increased, because by maintaining the constant mass. So here this structure is made, this particular structure is made to help the hydrokinetic turbine. This hydrokinetic turbine, this is the main shaft of this hydrokinetic turbine. Sometimes it is called the rotor arm. This total as a whole, this particular setup, this is called rotor, where these blades will be there and as well as this shaft will be there. Now here in this particular part, there will be bearing as well as there will be connection of the generator, where this mechanical energy, it will be converting into electricity. Now this electricity, it will be transferred through the distribution system, or it will be stored in a storing device just like your battery. That depends. Now if the speed of this, rotating speed of this particular rotor, it is not sufficient as per the conversion of this from the current of this fluid flow, so sometimes we need to increase the speed, rotational speed of this particular turbine. So how to increase? We can increase this rotational speed by using a gearbox. So that gearbox will also be installed. This gearbox consists of different size and shape of the gear, which will actually increase the rotational speed of this turbine rotor while it is connected with the generator. So in the middle part, that means shaft and generator, in between this generator, your gearbox will be installed. So you can see this is the picture of a real one which is installed in our laboratory. Here bearing is installed on this particular frame and there is no as such gearbox installed. This is the shaft and this is a plate which will be basically holding the turbine blade. So here this particular turbine, which is Darius turbine, I hope you have seen the classification of different type of turbine in the previous lecture. Or otherwise I will show you in my few lectures, because I have limited number of the lectures. So I will show you later how many types of different type of hydrokinetic turbine can exist. So here this is the turbine blade. This particular turbine blade, it is made of PLA, polylactic acid kind of plastic. So this is particularly we have designed this particular turbine and then we have 3D printed it through the 3D printing machine. So this is one of a kind, and this type of turbine you can use your own design and you can manufacture this type of turbine. So today's topic is what should be the material of this particular turbines, basically turbine blade. So here also you can see this is one type of turbine, Darius type of turbine. This is another type of turbine. This is called drag based turbine. And in this drag based turbine, there is the advancing blade, this is the retarding blade. That means if fluid is flowing in this direction, here in this particular figure, fluid is flowing from left to right, and it is striking this H-shaped curve. This H-shaped curve it will be striking, so this particular blade it will be rotating in this direction. Whenever it will be rotating in this direction, second one, this particular blade, it will be taking place of this the previous one. So it will go on continuing like this. So there are different types of design criteria, how and what should be the curvature. And here you can see this is the blade and this is second blade, and there will be some overlapping zone. This is the overlapping zone. Why overlapping zone? I will be providing overlapping zone. So there are different design criteria. Basically, we try to find out in which condition this turbine with available our resources, this particular turbine will give you the maximum efficiency. So based on this, we try to alter different parts of this turbine blade so that it can produce higher amount of the efficiency. So this is one of a design. This is another type of design. You can see this is another design and this is another type of design. There are lots of design. So differences between these two, this particular turbine, its shape is vertical axis, and this particular turbine is its horizontal axis. So this is called horizontal axis turbine, this is called vertical axis turbine. In this particular figure, this is also vertical axis turbine. In this particular picture, this is also vertical axis turbine. There are few advantage and few disadvantage of vertical axis turbine as well as this particular horizontal axis turbine. So basically, whenever we try to design or we think about any kind of hydrokinetic energy generation system, we have to keep in mind few criteria. First one, what will be the design? Second one, how I will be installing it? Third one, during operation, what should be the maintenance criteria, and if there is some maintenance problem, how we can resolve it? And then finally, obviously, there will be some economic criteria. So based on this, basically we will try to select different components of this particular turbine. So your turbine, it should be economically supportive, it should be on design perspective, it should be proper so that it can produce the highest amount of the efficiency, as well as during installation phase, it should not hamper the your environment. It should be easy. There also costing should be less. So different type of criteria will be there. Based on this, we generally try to select different parts of the turbine. So here material also one of that particular part. So if we see the specifically how material selection will be driven. So just I told you design configuration. In design configuration, basically this hydrokinetic turbine, it is almost replica of the wind turbine whatever you have seen in the real field. And if you consider that you are just putting this wind turbine into the water domain, so it will be, you can say this will be acting as a hydrokinetic turbine. But there will be some application difference because this particular turbine, whenever it is open to air, so its operating condition will be something different. When it will be putting into the water, its operating condition will be something different. So based on this, you have to consider some design characteristics for this particular turbine. So environmental challenges, because hydrokinetic turbine that will be always immersed into the water. So corrosive property you have to consider. So you have to select such a material which should not be prone to corrosion. Again, whenever water will be passing through a river or canal, so what will happen? This water may have a quality of very good quality, or it may be contaminated with the some corrosive property. So you have to check, you have to test for the quality of the water before putting your turbine into this particular site. So accordingly, you can select which type of material you will be selecting for your particular turbine. Now, performance factor. So suppose you are selecting a particular turbine material, but that turbine material property is something different, so that it is not suitable for giving good performance out of this particular material. So you have to select your material considering the performance point of view also. Now, rotor importance, the rotor actually converts the fluid kinetic energy into the mechanical energy, as well as its primary your design challenges will be hydrodynamic. That means when fluid will be passing through this particular rotor, if what will be the rotor shape, that actually will have importance on the performance of this particular turbine. So whether you are selecting a particular material, whether this particular material is easy to give that particular shape or not, that is also that may be also another problem. So before selecting a particular material, you have to ensure that I can give a shape of my desired design. So accordingly, you have to select your material. Now, some more thing, just like the material, it should have lighter weight, material it should have good stiffness, material it should have good strength, as well as material it should have good yield property, so that all those properties, it will give me the flexibility, so that this particular turbine, it will not break, it will not be prone to the erosion, because the fluid which is coming out of this natural river or channel, that will carry the silt. So that silt, whenever it will be impacting with the turbine blades, so it will be prone to erosion. So you have to select such type of material so that it will have certain toughness. And whenever this particular turbine you will be using on a particular flow domain, so what will happen, it will be keep on rotating. When it will keep on rotating, so this certain blade, it will after full circle, it will come to the again previous position. So what will happen, it will have a repetitive action, and repetitive cyclic stress will be applied on this particular part. So what will happen, the fatigue, it will be prone to the fatigue failure. So you have to select such a material where fatigue failure possibility also will be less. Your design should be such so that there should not be any sharp corner, so that there are two aspects. One will be the aerodynamic concept, another will be that particular sharp edge, it may be may generate for the stress concentration, it may prone to towards breaking because of this fatigue failure. So this type of aspects you have to consider whenever you will be selecting your material, as well as you are selecting your design. Moreover, I just told you that there are a few other things which will be present in this particular hydrokinetic turbine domain, that is biofouling. Biofouling, because those are the living organisms or microorganisms which will be developed on the turbine blade or turbine parts, which will be immersed into the water for a very long period. So you have to select such a material so that this biofouling can be removed, or the possibility of generating of this biofouling will be less. So those things also you have to consider while you will be selecting a particular material. As well as in your design, there must be some criteria whenever you will be selecting the design, so that the impurities which is carrying through this water, that should not be will be coming in contact with the shaft and the bearing. So some impurities should not block the bearing part. So those things, so for this you need to provide some strainer also in the upstream of the turbine. Okay, so this type of, there are different types of design modification and different types of material selection criteria always will be there. Now, whenever we are talking about the performance of a turbine, there are a few parameters which is actually driving those performance, this particular term. First one is the tip speed ratio for this particular turbine. Tip speed ratio, this is the ratio, you can see this is the ratio of the tangential speed of the tip of the blade divided by the fluid flow which is coming out of this particular river. So this tip speed ratio, it will also depends on the shape of this particular turbine. So this tangential speed of this particular turbine, that means this U, that will basically a multiplication of the rotor radius and multiplied by the omega. Omega, that means rotational speed which is being generated after striking the fluid on this particular rotor blade. So this is one parameter. Another is the coefficient of the torque. coefficient of the torque, this is the torque which you are getting in the turbine shaft, and the torque which is theoretically available in this particular corresponding to the stream, river stream. So there will be coefficient of power. So coefficient of power, this is the shaft power. That means when shaft is rotating, you can calculate or you can measure the power which is coming out of the shaft divided by the theoretical power available in this particular river. And principal moment of the inertia of this particular machine, this moment of inertia, that basically the your angular velocity multiplied by the moment of inertia, it will give you the torques. So this particular torque we are getting in this particular hydrokinetic energy turbine. Now if you see this particular flow chart, this flow chart is actually describing if we are handling a project, a hydrokinetic turbine, which we need to install. So starting from estimating of the capacity of the hydrokinetic turbine and implementation. So there are numerous number of the things you need to consider. First one is the study of the basic principle of the hydrokinetic turbine, and then selecting the turbines. Say here we have considered we are considering a Darius turbine. So now what will be the design parameter of the Darius turbine? So different parameter will be there. Now there will be design parameters, there will be different mechanical component, there will be flow parameters. That flow parameter is corresponding to the river flow. Now there will be different electrical components. All these things, again, if you see the design parameter, lots of design parameter is present in case of the Darius hydrokinetic turbine. The solidity, number of blade, tip speed ratio, already we have discussed. Aspect ratio, that means the ratio of the diameter and height. So overlap ratio, that overlap ratio you have seen, I have shown you already a drag based turbine where two S shape of one will be basically, if we are placing it like this, there is no overlap. If we are placing it two blades, so there will be overlap, that much amount of the overlap. So angle of attack, so if we are considering what will be the angle between the blades as well as the fluid which is coming, so that will be the angle of attack. Helical pitch of the angle, that means some of the turbine, if we consider this particular bottle as a turbine, so we can consider this is the straight. Now if we twist it, so if we just hold it and twist it, so its blade will be twisted. So how much will be the twisting angle? All these things has been developed because of certain purpose. Purpose was to produce maximum amount of the performance. So apart from this, there are many other things. So all these things you have to decide corresponding to your requirement, and after that we have to go through the techno-economic analysis. So after techno-economic analysis, that means this particular energy generation system, how much energy will be generated, how much cost we have already given, and if certain amount of the energy is being generated. Now if we sell it to the consumer, so what will be the revenue, then ultimately how much will be in our hand. So all these things we have to consider, and then we have to select different components. So just we told you that moment of inertia, this is also contributing towards the material selection. Basically moment of inertia, it has been observed that if material is lighter, it will help the turbine to rotate faster. So if material is heavier, so it will hamper the turbine to rotate at the very beginning of the rotation. So in generally we call it self-starting of a particular turbine. The self-starting torque, this is a premier issue of certain type of turbine, mostly drag based type of turbine. Drag based type of turbine, that means those type of turbine which you have already seen. I have shown you this picture. So here what happens, the certain extra amount of the torque is required to rotate it initially, so that your material should be such so that it will not create any hindrance of rotating this particular turbine. So always this lighter type of material is preferable, so that those type of self-starting torque problem can be removed. So far we have discussed about the performance. So, and I have told you that what are the different performance parameters. So if we want to represent it through graphically, so you can see that in this lower part, that means this x-axis, here it is written as tip speed ratio, and in the upper part here it is written as coefficient of power. So in general, for this type of machine, we represent our performance curve as CP versus TSR. So this is one representation technique, performance representation technique for this type of hydrokinetic turbine. Now CT, that means coefficient of torque, versus TSR, that means tip speed ratio, that may be another representation. So two representation, CP versus TSR and CT versus TSR. These are the two representation usually we prefer to represent how much the performance is giving by this particular turbine. Now here you can see multiple number of curves are present. First one I used to tell you, this is the green curve. This particular green curve, it is basically giving a maximum extent or maximum limit of efficiency. This is called Bell's limit. This Bell's limit, if you see this particular value, it is almost 60%. So basically 59.3. So this 60%, that means if you place a turbine in a natural river or natural fluid flow, so you cannot get more than 60% efficiency, whatever may be your design, whatever may be your turbine. So there are some derivations, some theory is there. So that theory is given by a researcher who is Blake. So he told that maximum 60% efficiency can be achievable through this type of turbine. So why we should use this type of turbine? Because if we go for conventional turbine, conventional hydro turbine, their efficiency you can get more than 80%, 90%. So why we will go for this particular turbine? Basically, this type of turbine, it is called zero head turbine. That means here, when river flow height, it is very less, even less than 3 meter, 4 meter. That means we can put this type of turbine in a normal canal also, where water depth is very late, 2 meter, 3 meter, that is more than enough. Here main concern is how much speed is available, water speed is available in this particular canal or channel. Now this type of turbine, whenever you will be installing, you have already seen civil structure is very minimum. So when we are not using any civil structure, that means we are not hampering the environment. So the flora, fauna which are present, we are very minimum hampering them. So environmental impact is less. So whenever we are installing this type of turbine, so civil construction is less. So basically possibility of earthquake, which is that is also less, which is basically present in case of the big hydro energy turbine where dam is being installed. So because of all this purpose, we this particular turbine is selected for install. And drawback of this particular turbine is efficiency is less, and the quantity of the power generated by this particular turbine, that is also less. And we are completely dependent on the water of the channel, and whenever water is available, then only this particular turbine will be rotating and energy will be generating. So what will happen? So you have to, if you want to provide your consumer a constant electricity, so you have to you have to keep the provision of energy storage, that means battery, for this particular turbine. And since this particular turbine, constant speed of the river flow, I cannot ensure constant speed of the river flow. So constant rotation also I cannot ensure in this particular turbine. So the frequency of the electricity which will be generating through this particular turbine, that is also will be fluctuating. So you have to consider all those things, and accordingly you have to choose your device so that ultimately constant frequency can be given to the consumer. So this type of modification is required for this particular type of turbine. Now here you can see different models, and corresponding to these different models, different performance curve is here. This is the first performance curve. This is corresponding to a Savonius hydrokinetic type of turbine. And this Savonius hydrokinetic turbine, it is called drag-based turbine. This is also drag-based turbine. This is also drag-based turbine. This is lift-based turbine. This is lift-based turbine. Again, these are lift-based turbine. Differences: this is two blade. This is multiple blade. More number of the blade. Here 4 number of the blade, and here 3 number of the blade. But this is a Darius turbine. If we get a cross section of this particular blade, we can see aerofoil is present here. But if we take a cross section here, we will not. You will see the uniform cross section will be there here, as well as here. So these are all drag-based turbine, and this particular turbine, all this type of turbine, these are lift-based turbine. Differences of this and this, and their number of blade will be something different. As well as if we see the differences, this and this 3 turbine, it is the horizontal axis turbine, and this is vertical, this is again horizontal, this is horizontal, this is vertical. So in this manner we can classify different type of turbine, and there are some other classification criteria also, and based on this, those type of turbine can be classified. So again we are coming back to the material of the turbine. This material of the turbine, if you I told you that there are certain criteria. One of the criteria is the weight of this particular material. We wish to select that particular weight should be lighter. Density and the weight, density and this factor is if lighter material is selected, so rotational speed will be getting, that will be more. So its strength should be higher, its stiffness also should be higher. Its corrosion resistive property should be there, and before installing this particular turbine in a particular channel, we must have the water quality test result. So accordingly we can select the material of this particular turbine. Fatigue resistance, already have seen. Fatigue failure will be occurring when repetitive cyclic stress will be generated. So it is bound to be happen, because every time your blade will coming into the same position, that particular blade, it will have a load on this particular blade. When this particular blade, it is basically fixing with the shaft as well as at the end of this blade everywhere. So manufacturing consideration. Suppose you have selected a particular material, and as per our requirement, say density and weight, it is also good, say strength and stiffness also good, say it is having anti-corrosive property, say it is having less probability of getting fatigue failure, sab theek hai, everything is good. But whether I can mold this particular material to my desired shape or not, and to make this particular material to my desired shape, because I have designed my drawing, my turbine design. So how easily I can make this particular shape, that is also another criteria. So this manufacturing process, that is also very much important while you are considering a material. So you can see these two pictures. One is basically producing this type of aerofoil cross section here, and another is put here, this aerofoil cross section bed, it is put it in a this is basically tidal turbine, marine turbine, and it is put it in a particular submerged condition. So it has been shown as submerged condition. So there are very favorable material, very popular material. One is aluminium, steel. Again, if we go for the difference between aluminium and steel, steel is stronger, but aluminium is lighter. Aluminium is easy to give the desired shape, and in case of the steel, it will be comparatively difficult. Composite material, if we consider composite material again shown the better performance than these two. So composite material, fiberglass material or carbon fiber material, that has been shown that this particular composite material can be used for this type of turbine blade preparation. But there are different types of composite blade also. So what should be the orientation of the laminate of this particular composite? That is also main criteria. Which type of combination you will be selecting, that is also another criteria. Whether preparation of this particular composite is suitable or not, whether those particular composite will be able to sustain for a long days while we will be immersing into the water. That is also another criteria. So all these things you have to consider. Again, blade design optimization, in order to get its maximum hydrodynamic performance. Basically, we provide a particular shape of aerodynamic to a particular turbine blade. So to get this particular shape, whether the selected material will perform best or not, whether the manufacturing technique we are adopting, that will be giving me that particular freedom so that we can make those type of shape or not. Those are the criteria. Operating environment, I just told you what should be the flow rate, because if flow rate is maximum, so the load which is be falling on this particular blade, that will be also in the higher side. So the composite you are considering, whether that will be capable of composite or material you are selecting, that will be capable of withstanding those load or not, that also you have to consider. So sediment level, what will be the sediment level? So what will be the size of this particular sediment? In general, sediments parts per million. Sediment, we measure sediments parts per million. So what will be the size of this particular sediment particle? So in terms of the micrometer. So micron, actually in terms of micron. So if what will be the shape of this particular sediment, there is a term called shape factor. So whether this particular sediments, it is having a very piercing sort of, whether it is round shape, whether it is having some sphere sort of shape, so that whenever it will be impacting with the same velocity, say your fluid velocity is same, but the shape of the sediment is something different. One is round, another is having some sphere sort of shape. So the sphere sort of shape sediment with the same velocity, when it will be impacting on the blade, so it will have more abrasion on this particular blade. So before going into the installation of this particular turbine, you have to first check, you have to take the sample of the sediment throughout the year. Basically, before installation of any such type of energy conservation device, you have to have at least 1 year data. So you have to analyze those 1 year data for water quality, for sediment, as well as the reliability of getting water flow throughout the year, even throughout the day, and for which purpose you are installing this particular energy generation system. That means whether you wish to provide electricity for a peak time, or you wish to provide electricity for a base load. So that will also be very much important while you are basically cross-checking that what is the reliability of getting certain amount of the water in a particular river. For this, another type of graph is generally being prepared, that is called flow duration curve. Flow duration curve of a particular river. So a certain time series data is basically collected. That means the data with a particular time. That particular time, it may be hourly data, it may be daily data, it may be 10 daily data, it may be monthly data. That means one data in 1 hour, one data in maybe 10 minutes. So we will call it 10 minutes data. One data in per hour. That means we can, so in a particular day there will be 24 number of data. So through this particular data, you can give some impression. You can tell that in a particular day, how much amount of the time I can ensure that that much amount of the water is present in my river, so that I can go for design of this particular turbine. So this is a small scale data analysis. If you are going for higher scale data analysis, suppose, then you have to consider the whole year data. So whole year data, so what you will do, you will collect daily data. So in a day, once you will be collecting the data, so daily how much at least how much water you can ensure, that particular exercise you can done. So flow duration curve is there. Through this particular curve, you can ensure that that much amount of the water is present in a particular river. So correspondingly, you will be selecting your material also. That means that amount of the, for this particular amount, basically you will be designing your turbine, and correspondingly you will be selecting your material to withstand that amount of the load. If your design is somehow in the lower side, so it will break. That means if you have found out that your fluid flow, suppose your fluid flow, you are considering that this will be 0.5 meter per second. So based on this, you have suppose designed your model, and after preparation, after implementation, what you have found, suddenly 1.5 meter or maybe 2.5 meter of water you are getting throughout the day. So it may happen that your turbine may break. So corresponding to 0.5 meter per second, you have calculated that much amount of the load will be withstood by this particular turbine blade. So accordingly, you have selected your thickness of your blade, you have selected your material, that okay fine, that much amount of the load it can withstand. But suddenly you have found out it had become 4 times, 5 times. So you have to check what will be your factor of safety of this particular material, whether that can withstand this particular amount of the fluid velocity which is present in the river or not. So that particular analysis also you have to perform before implementation of your turbine. So those are the things. Now, in general, the material we use, we have seen that there are lots of material can be used, but commonly used material is aluminum alloy, synthetic material, or composite, or natural fiber. These are the material. Again, those criteria is low density, high mechanical strength, high modulus of elasticity, high capability of the absorb of the energy, high chemical and environmental resistance must be there. You can see here are 4 photographs. You can see first one here, they have basically selected some natural material, that means wood. They have prepared some blade. This is one blade through wood, because the preparing of this particular blade through wood, this is kind of easy. That means workmanship is easy. But if you put this particular wood material into the water, it will be problem, it will not work. So you have to provide some coating here. So then only you can put it into the water, but still that is not popular in case of the hydrokinetic turbine, because reliability of this particular coating, it will be questionable. Now there you can see there is some metal, and this particular metal, it may be some aluminum alloy. This is composite. This is also composite material, and this is a horizontal shaft tidal turbine. This is also horizontal. Actually, shaft is not present. This mechanism is something different. And this particular blade, it will be installed on a shaft. This is also horizontal shaft hydrokinetic turbine. So you can see here also another blade they have prepared, and this is prepared in a CNC machine. So you have to arrange for higher cost to prepare this type of machine. This has been prepared through this alloy, this aluminum magnesium silicon alloy. So its name is AA6061T9, and second one is 6082T6. So these are the different aluminum alloy has been considered for it. They are better selected for their particular immune to corrosion, higher mechanical strength, higher yield strength. For this particular reason, that has been selected. But again, the manufacturing cost is higher, but we will get a very precise blade profile, so that it can generate higher amount of the performance. So another thing is synthetic fiber reinforcement composite. So synthetic fiber reinforcement composite, this type of material in generally been used for their durability, corrosion resistance, and high strength to weight ratio, stiffness, damping properties. That means even if higher amount of the load, just I told you one case that you have considered, you have designed your particular turbine for a lower amount of the fluid flow velocity, suddenly it has got the higher amount of the fluid is coming. So how much energy, additional energy it can absorb. So that particular property, it must be there through this flexural, what will be the flexural strength, what will be the stiffness, what will be the damping properties, damping property because to damp the vibration which will be created because of the some bearing fault or something. And now fatigue resistance, that means this cyclic stress which will be generating this fatigue load, so how it will be basically considered. And customability, that means this particular synthetic fiber reinforcement composite, this can be easily custom to my desired shape. So these are the reasons, so this type of synthetic fiber also will be considered. So there are different manufacturing techniques. One just hand layup, another is vacuum infusion, resin transfer modeling. These are the more popular manufacturing technique through which this type of synthetic material is generally being prepared to make a this hydrokinetic turbine blade. Again, what will be is laminate construction, whether fiberglass or carbon fiber will be used for these things, or whether it will have a radial reinforcement or unidirectional reinforcement. Based on this, basically its strength will be depending. So which type of resin you will be using, whether you vinyl ester, polyester, epoxy, which type of resin you will be using, and if what should be the viscosity, what should be the pot life, that means the resin, how much time it will be in your during manufacturing it will be there. So all these things are very much important while you will be selecting a material. Suppose by observing a material property, suddenly you cannot decide that that particular material will be suitable, because suppose you have designed and you have found out there are few design parameters, that particular design parameter magnitude also you have got, and accordingly you have matched some of the material. But whether that particular material, through this particular material, is it easy to prepare those kind of shape which is desired or not, that is also a main problem. So that also you have to consider while you are selecting. So in this particular figure you can see, just I have shown you earlier also. So there are a few natural materials just like wood. So we can select those particular material to prepare those turbine blades. But again, we have to provide some of the coatings. This challenges, main challenges will be while we are using this type of material, that means wood. So it is very difficult to give a proper shape, which is basically desired to get highest amount of the efficiency, because there that workmanship will be should be very precise. But if we are using CNC machine, so then we can get exact shape whatever we have drawn. So there is some example comparison of different material. This Pinus radiata, this is one kind of fiber, natural vegetable fiber, which is actually available in Brazilian Amazon forest. And this is e-glass fiber, epoxy resin, and composite reinforcement e-glass. Mass per rotor, in case of the kg, you can see this will be kind of heavier, and e-glass fiber it will be kind of less heavier, and epoxy resin further less fiber. And elastic modulus, if you see elastic modulus, e-glass fiber, it is having a 6.4 kg mass, where you will be getting this much of gigapascal of the elastic modulus, where this Pinus radiata, here you will be getting the less amount of the electricity modulus. So in this particular case also you can see that the e-glass fiber or epoxy resin, all these type of materials, these are much more superior rather than this natural material. But still natural material we generally use in order to ensure the sustainability of the material. Sustainable material, that means that can be sourced from the nature, and it can be used, and these particular things will not be depleted. So this sustainable materials, to find out the sustainable material, that is also very much important. So different combination is being made to prepare those type of sustainable materials which can be used in the preparation of this hydrokinetic turbine. So again, you have to select such a material which will be easily available, and availability of this particular material, that will not hamper its availability, as well as it can be easily used to give a particular shape, and its performance will be better. So this type of turbine you can this type of material you can see e-glass fiber, it will look like this fiber fabric and polyester matrix. These are the three main example of this type of synthetic fiber. There are many other synthetic fiber also present, and that can be used for those preparation of this turbine. Now, if you see all these things we have discussed, there are different type of, mainly we have discussed natural fiber or natural material, or we have discussed about the different metals, and we have discussed about the composite, we have discussed about the synthetic material. But still people are basically trying to find out some more new material to prepare these hydrokinetic turbine blades or hydrokinetic turbine different components, because each and every material we have discussed so far, there are some drawbacks. So considering the drawbacks, people are trying to find out that what will be the new material. So for this, basically the main criteria is the what will be the performance criteria, what will be the manufacturing criteria of this new material, how easily it can be manufactured, what will be the strength of this particular material, whether this particular material can be sustained long. Basically, whenever this type of energy conversion system is being generated, so this will be generated in view of using it 20 to 30 years. Conventional hydropower plant, it is for more number of years, but this type of plant is for 20 to 30 years. So whenever we are going for 20 to 30 years, whether those type of material will be suitable or not, whether it will be economically viable, whether this particular turbine, it can be replaced, that means it can be easily suppose we are selecting such a material, that particular material is not readily available in the market, or to prepare those particular material, say it is you have to prepare a new mold every time, so then it will be difficult for a manufacturer to consider those particular material in commercial point of view. The cost we are using for to preparing this particular material, that should be also within the limit, so that energy production cost should not exceed and should not actually our energy production cost, it should attract the consumer. That suppose if we have solar energy, if we have our some other form of the energy, and if we have this type of hydro energy, so the energy cost per unit, that must be within a range, so that a consumer will be selecting those type of energy. Otherwise it will be difficult to sustain in the market. So already we have discussed, so these are the consideration for material selection of turbine blade, and mainly nowadays people are trying to use a biodegradable type of material, so that it can be it will not have any impact on the environment. So this is the latest area of research to find out or to prepare a synthetic material which also will be biodegradable, and that is easily available, that should be sustainable. So people are trying to find out those type of material, and trying to use this for a hydrokinetic turbine as well as wind turbine. But the condition for using those material for wind turbine and this hydrokinetic turbine, this will be completely different. There are some similarity, there will be some dissimilarity. So with this, basically people are trying to select those material. Basically this hydrokinetic turbine concept that has been arrived from the wind turbine. The most of the design they have considered it from the wind turbine, So in every instance, it has been observed that the technology that has been generated in case of the wind turbine, that actually later been adopted for the hydrokinetic turbine with a certain modification mostly for the fluid medium, modification mostly for this corrosion properties, and modification mostly due to some other aspects. Just like if we consider the wind turbine, in case of the wind turbine, the availability of the wind is certain kind of random. But whenever we are talking about the hydrokinetic turbine, this hydrokinetic turbine availability of the water is more certain than this particular wind turbine. Direction of the wind, that you cannot predict, that can change anytime. Direction of the water which is available in the channel, that is kind of certain. You can tell that the direction of the water from in a particular channel, this will come from which direction to which direction, because that is bounded in a channel. But direction of the wind, that will be something different. Wind turbine, its size will be something bigger. Hydrokinetic turbine, that will not be bigger, because I have already told hydrokinetic turbine that will be installed in case of the small water depth, 2 meter, 3 meter, maximum 5 meter. You can go for higher water depth. So the size of the turbine for the hydrokinetic turbine, that will be comparatively less. Even if you look the similar design of the hydrokinetic turbine and similar design of the wind turbine, that will be looking like same. But the size wise, wind turbine will be bigger, size wise hydrokinetic turbine will be lesser. So there are different factors. All those factors basically will be compelling you to consider the design as well as selection of the material. So similar type of design, say Darius wind turbine and Darius hydrokinetic turbine, if you see both of these two, it both will be looking like same, but considering its size, hydrokinetic turbine will be lesser, smaller, and so its strength will be lesser. But in case of the wind turbine, its strength should be requiring higher order. So the material you will be selecting, that will also be, you have to consider accordingly. Again, the corrosive property also present in case of the wind turbine. Corrosive property, corrosiveness, that particular problem, that will also be present in case of the hydro turbine. But in case of the hydro turbine, that will be higher. In case of the wind turbine, that will be lesser. So your concentration of the selecting of the particular material in corrosion point of view, you have to be more concerned for the hydro turbine rather than the wind turbine. So there are different factors, and considering the property of the material, ultimately you have to select those material which will be suitable for your turbine. So with this, would like to end up our presentation, and these are the different references I have collected while I was preparing for this particular presentation. Few photograph I have taken from the Google, and that is means you can also see, means that is freely available in the Google. So thank you, and